Hello. So let's continue with probabilities. So we want to look at the multiplication rules and conditional probability. Okay, that is what we want to look at next year. So the multiplication rules of probability can be used to find the probability of two or more events that occur in sequence. All right, they occur in a sequence. You can use the multiplication rule to do that. For example, if a coin is tossed and then a die is rolled, right? So you have these two events: toss a coin and roll a die. We can find the probability of getting, for example, a head on the coin and let's say a 5 on the die. So the multiplication rules of probability helps us to find such probabilities. Okay. So in this case, the two events are said to be independent. The outcome of one does not really depend on the other one. Tossing a coin and rolling a die are totally independent events. One does not depend on the other or the outcomes. Okay. So the outcomes of the first event does not affect the probability outcome of the second event. So they are independent. Okay. So two events is the definition. A and B are independent if the fact that A occurs does not affect the probability of B occurring. Okay, then you say that those two events are independent. Okay. Okay, good. So the first rule of multiplication says that when two events are independent, then the probability of both occurring is given by the product of the first probability multiplied by the other probability. Okay, probability of A and B occurring is given by this product. All right. So let's look at the example we mentioned before. A coin is flipped and a die is rolled. Find the probability of getting a head on the coin and a 5 on the die. Okay. Because the events are independent, we can just find the probability of getting a head, probability of getting a 5. So this is a 5, not 4, even though the probabilities are the same actually, right? Probability of getting a head is 1 out of 2. Probability of getting a 5 or even a 4, is 1 over 6. So if you multiply, then you get 1 over 12. Okay, so that gives you the probability. You could do it using sample spaces as well. All right. So this is an alternative way of doing that. So if you flip a coin, you are getting a head or tail. We know that. If you roll a die, you get 1, 2, 3, 4, 5, or 6 showing. Okay. So if you combine this and that, you're going to get the sample space for the events. The sample space will be either a head showing in a 1 on the die, head or 2, head on the coin, and then 3 on the die, up to this. You could also have tails. And so all of this will be the sample space, okay, for the events. The sample space, you have 12 elements in there, okay? So the probability of getting a head and 5 will be this guy here, H5, which is just 1 out of the total of 12. So the probability is 1 over 12, which is the same as what we got here. Okay. But now using this formula is much easier and simpler because you can imagine that if these events were more extensive, right? If you had a lot of outcomes in this one and also a lot here, this would be a very long list. Okay. And it would be difficult to set up the sample space. So it's easier to apply that anyway. Okay, good. Okay, so here's another example. A card is drawn from a deck and replaced. Okay, the replacement is important. Then a second card is drawn. Find the probability of getting a queen and then an ace. All right. If you don't replace, I think we've discussed this already. If you don't replace the card, okay, then the probability of the second card will depend on the first trial. Okay, but when you replace it, then the events become independent. Okay, So what is the probability of getting the queen and ace? Okay, you have a queen, and then the second time you get an ace. So probability of the queen, we have 4 queens in the deck. So we have 4 over 52. We have 4 aces as well. So probability of an ace would be 4 over 52. When you multiply them, you have 16 over 2704, which is 1 over 169. Okay, so that gives you that probability. Okay, good. So for independent events, that's what you do. Okay, you can apply the same rule to not just 2 events. You can apply it to 3 or more events. Basically, you just keep multiplying, right? So you can extend it to 3 or more independent. As long as the events are independent, the probability of A and B and C and let's say K occurring will just be the product of their individual probabilities. Okay, so that is how we apply. Okay. This says that this is an example. Approximately 9% of men have a type of color blindness that prevents them from distinguishing between red and green. Okay, this is a reality. Okay, so when you write papers and reports and stuff, you have to be careful about not using red and green. You use maybe red and blue or green and blue. If you combine red and green, some people can't recognize the difference. So this is reality. Okay, that's a color blindness. Now, if 3 men are selected at random, find the probability that all of them will have this type of red-green color blindness. Okay, the probability is 9%, right? 9% of men have that color blindness. So what is the probability that the first guy will have it, the second will have it, and the third will have it? Okay, so probability of C represents the red-green color blindness, and C will be the product. Probability of C having it, the first one, the second man, the third man. So you just multiply all 3 with that. Okay, then you round this to 4 decimal places. That gives you that. So it's tiny probability. Okay, good. Now, when the occurrence of the first event changes the probability of the occurrence of the second event, then the 2 events are said to be dependent on each other, right? The events are dependent because one affects the other one. Okay, so suppose if you draw a card from a deck, all right, and you don't replace it, and then you draw a second card. The probability of the second card will depend on the first event because the number of cards have now reduced, if you like, from 52 to 51. Okay, so question is, what is the probability of selecting an ace on the first card and a king on the second card? All right, so these events will be dependent on each other if you don't replace it. So dependent events by definition is when the outcome or occurrence of the first event affects the outcome or occurrence of the second event in such a way that the probability is changed. The events then are said to be dependent, right? So examples of dependent events would be that, if you like, these are like, simple practical examples of these. Having high grades and getting a scholarship, they are dependent, right? So oftentimes scholarships are given to students who have high grades. So if you have high grades, you're likely to have scholarships, so they are dependent. Parking in a no parking zone and getting a parking ticket, they depend on each other. You don't get a ticket if you don't park in a no parking zone. Drawing a card, we've talked about this. If you don't replace it and draw a second card, right, those events are dependent, okay? So you can think of more dependent events as well. Okay, now consider the problem where a card is drawn from a deck and it is not replaced. We're doing an example of this. Then the second card is drawn The probability of selecting an ace on the first draw, of course, is 4/52. We have 4 aces, and we have a total of 52 cards, so 4/52. Now, the probability of getting a king, okay, in the second draw will be, we still have 4 kings remaining, right? But the total number of cards is now 51 because we have selected an ace already in the first draw. So the total number has reduced. So the probability of getting the king in the second draw is 4/51. Okay. Okay. So again, now if the first one was also a king, remember, then we are going to have here 3/51. Okay. All right. So let's deal with this. Now, by the multiplication rule, the probability of both events occurring, that is drawing an ace in the first case and then a king in the second, will be the product of these two probabilities, right? 4/52 multiplied by 4/51. And that gives you this number here. Okay. So we say that the event of getting a king on the second draw, given that an ace was drawn in the first time, is called a conditional probability. Okay, getting the king the second round is conditioned upon you drawing something, the ace, in the first one. So that is a conditional probabilities. Conditional probabilities are very important. Okay, so you pay attention to them. Okay, so the conditional probability of an event B in relationship to an event A is the probability that event B occurs after event A has already occurred. Okay, so the notation for conditional probability is given that. So that is the probability of B occurring, given that A has already occurred. This is not a, okay, this is, you are finding the probability of B, but this guy has already happened. This event has already happened. Okay, so that is a conditional probability. Okay, good. So in the card example, okay, PBA is a probability that the second card is a king, given that the first card is an ace. Okay, so probability of a king, given that the first is an ace, will be 4/51. Okay, this is to show that the probability of finding a king is not in from the ordinary deck per se, because you have already taken a card out of the ordinary deck. Okay, so it's now a conditional probability. All right, good. Good. So multiplication rule 2 says that when two events are dependent, okay, that is when you have conditional probabilities and stuff. When they are dependent, then the probability of both occurring is this. Probability of A and B will be the probability of A multiplied by the probability of B, given that A has occurred. Okay? That is when they are dependent. If they are not dependent, you don't need this, right? You just multiply their separate probabilities. But now this has occurred. The occurrence of this one depends on the fact that this has already occurred. So you use a conditional probability. Good. So here's an example. In a shipment of 5 microwave ovens, 2 are defective. Okay. If 2 ovens are randomly selected and tested, find the probability that both are defective if the first one is not replaced after it has been tested. It has been tested, okay? After it has been tested. So this is important. If you replace it, then it's not dependent, right? But if it's not replaced, then you have to think of conditional probabilities. Then the events are dependent events. Okay. So probability of the first one being defective and the probability of the second one being defective. Okay. So these notations are the 2 defective microwave ovens. So you find the probability of the first one being defective, multiply by the probability of the second one being defective, given that the first one was already defective. The first one is easy, is probability. There are 2 microwaves which are defective. So that probability is 2 out of the total. So 2/25. Now the probability that the second is defective will be 1 out of 24. Okay, because you have already taken 1 out. So the remaining is 24 defective ones. And you will only have 1 defective one left as well. So 1/24. You multiply them, you get 1/300. Okay, so that gives you the probability of the 2 defective items when they are taken in sequence. All right, this one is selected, and then the next one is selected without replacement, of course. Okay, so you can just manipulate this formula, right, to get a conditional probability. This is just mass. If you divide through by P of A, probability of B given A will just be P of A and B divided by P of A. Okay, so that gives us this. So the probability that the second event B occurs, given that the first event A has already occurred, can be written as this. Find the probability of A and B divided by the probability of A. Okay, that gives you the conditional, the formula for conditional probability. Okay, so let's do some examples and bring this to a close. So a survey asked 100 people if they thought women should work as driver's mates, right? Truck driver's mates. Okay, so these are people who follow a driver, commercial truck, commercial car, and they take their fare on behalf of the drivers. So they are the truck drivers mates. Okay, usually they are guys, all right? So question is, a survey asked 100 people if they thought women should work as truck drivers mates. These are the results. Okay, for the males, 32 said yes, 18 said no. For the females, 8 of them said yes, females can. 42 said no. Women shouldn't do that work. Okay, so you want to find these probabilities. Find the probability that the respondents, people who responded to the survey, answered yes, given that the respondent was a female. Okay, and then you want to find the probability that the respondent was a male, given that the respondent answered no. Okay, how do you find those probabilities? Well, so let males be M, let females be F, let those who said yes be Y, and let those who said no be N. The first question is asking us to find the probability that the person said yes, given that the person was female. So Y given F, that's what we want to find. We want to find the probability of Y given F. By the formula for conditional probability, this probability is the probability of F and Y, those who said yes, who are females, or the females who said yes, divided by the probability of the females. That will give us the first one. All right. So how many females said yes? There were 8. So the top will be 8. How many females? Probability of females. Females, total number of females were 50, right? 50. So you divide by 50. So 8 out of 50 will give us this probability. Okay. So that is given by this 8 out of 50. Okay. Or like 8 out of 100, but 50 out of 100, that's 8 out of 50 over 25. The second question is asking us to find a probability that the respondent is a male, given that they answered no. So we want to find M given N. All right. So we want M given N. And by the formula for conditional probability, that will be the probability of the males who said no, divided by the probability of all those who said no. All right. Okay. So probability of the males who said no will be 18 out of 100. Probability of all those who said no is 60 out of 100. If you divide, right? If you divide, you're going to have 18 out of 60 or 3/3. And that gives you this conditional probability. All right. So that brings us to the end of probabilities, the introduction to probabilities, really. The next set of of lectures, we'll look at discrete probability distributions. Okay, so you can try your hands on some of these exercises. All right. Yeah, just 2 exercises. Okay, so I'll bring this to our end, and then we'll do the other ones later on.